right, we have one more case study, and then it's sort of a little bit of a surprise to close out the day, so stay put. It is my pleasure to introduce to you SAPA, and really glad to have you here. Ignacio, you're going to present the whole story, so we appreciate it. Thank you.
Thank you very much. Okay, good afternoon to everyone. My name is Ignacio Lizazu, and I am Head of Planning in SAPA. With me today, it is here Aitor Urretavizcaya, which is the Operational Model Development Manager. And well, first of all, I am aware that I am the last presentation of the day, so I will try to make it as fast and significant as possible. It is difficult to sum up in 30 minutes, which has been our redefining of the operational model. But I will be happy if at least at the end of the presentation you have an overall idea of what our journey has been. Well, this is the content of the presentation. We will start by talking a little bit about SAPA because I'm pretty sure that most of you don't know about us and about what we do. Then we will talk about the BCR 8x8 production program, which has been the program that really has initiated all of this operational transformation. Then we will try to analyze a little bit our product structure on the 8x8 Power Pack, which is really complex to manage, and we will see why. Then we will talk about the new operational model that we have implemented and that we continue implementing at the moment. Then, as we are in the demand-driven world, we need to talk a little bit about demand-driven. So we will talk about how we have implemented demand-driven in the planning model. Then we will talk a little bit also about our machining plan and how we have introduced several demand-driven principles to manage our machining plan. And last of all, we will talk about some major operative results. So, about SAPA. We are a company which is specialized in designing, manufacturing, and distributing automatic transmissions and power packs for heavy vehicles. Heavy vehicles for the defense sector. Okay? We have two main facilities. One is located in the Basque Country, in the north of Spain, which is SAPA Operaciones. In SAPA Operaciones, we are around 350 employees. So, as you can see, we are little compared to the huge companies that today have presented. In SAPA Operaciones, we have our engineering department, where our product is fully designed and developed with a department that is made up of more or less 100 engineers. And we also have our assembly lines and our machining plant. Something special about SAPA Operaciones is that it is one of the eldest companies in the country. It was founded in the 16th century and has always been related to the defense sector. During its history, it has varied the products manufactured, but has always been really close to the defense. And for the last 25 years, we have own product, which is the automatic transmissions and the power packs. Then we have our American facility, which is located in Michigan. It's in Shelby, near Detroit. And for the last 20 years, we have been working with the US Army in low-rate prototype production transmissions for developing technology and for improving the mobility systems in the Army for the next years. We have a wide product range. First, we have our tracked vehicle transmissions, which are the ACT family, Advanced Combat Transmission. Those are 32 years automatic transmissions. And depending on the weight and other characteristics of the vehicle, we have the ACT A50 for vehicles for around 35 to 55 tons. And we have the ACT 1075 for vehicles of nearly 75 tons. Then we have our wheeled vehicle transmissions, which are the SW family of transmissions. There are also 32-year transmissions, and those are for wheeled vehicles. Then, another important thing is that we have developed power pack integration technology in which we take our transmissions and we integrate it in a whole power pack. This power pack is made up of an engine, the transmission, electrical generation system, hydraulic systems, and so on. This power pack will be the equivalent of what you see when you open the hood of a car. Everything that you see below that hood is that power pack. But in this case, this is for a tank or for a defense vehicle. Then we also develop electrical generation systems, as for example, the auxiliary power units that we attach below the defense vehicles. It's important to say that we have own technology, we have own product, and we have end-to-end technology know-how. Our technology nowadays is really cutting edge and truly benchmark in the sector, and we continue growing and improving our technology. BCR 8x8 program. Okay, this is the production program that really initiated our journey and the travel that we have been going through for the last 5-6 years, more or less. It was the biggest challenge ever for the company in terms of production and operations. And the program needed of the production of 100 vehicles for the Spanish army. The vehicle is this, that you can see in this picture. It is called the Dragon 8x8. It's a wheeled vehicle of around 25 tons with 8 wheels, and it's all-wheel drive. That's why we call it the 8x8 Dragon vehicle. And SAPA is responsible of delivering the power pack for this vehicle. At the time we signed this contract, that was around the year 2020, the company had the capacity for producing around 1 power pack per month. And the program needed, in some production phases, to deliver even 8 power packs per month. So the challenge for us was really immense. Okay, analyzing the power pack a little bit, you can see that it's really, really big. We are talking about a system that is more or less 2 meters tall and nearly 2.5 meters of width. And it's composed, as I have said, of the engine, our transmission, that is the SW624, the fan system, radiator, and the SISGE, that is the electrical generation system. Analyzing the structure, you will see why it's so complex to manage. We have a structure that is made up of nearly 1,300 SKUs, which are different elements. And in total, we are talking about 10,000 parts per power pack. If we analyze this structure from a supply and production strategy perspective, we'll see that 3% of the elements in the structure are assembly references. Nearly half of the structure is outsourced references. And then there are several references that we have decided to internally machine in our machined plant. Those references are for the transmission and represent the 21% of the structure. For producing these 21% of references, we also have an 18% of raw material and rough machining references. And then we also have commercial element trays, which are commercial kits made up of bolts, joints, washers that we order in kits and we deliver to the assembly line. If we analyze the structure from the cost perspective, we will see that it's a really non-balanced structure. We have made a categorization of the elements. We have A+, A, B, C, and D elements, depending on the cost. And you will see that in the 9% of the most expensive elements, which are the A+ elements, we have nearly the half of the cost of the total product structure. In the A elements, which also are more or less the 9% of the elements, we have nearly the 20% of the cost of our product structure. So in the 18% of the elements, there is nearly the 70% of the total cost of our structure. Depending on this cost category, we have some rotations that we have defined. In the case of the A+ elements, we rotate them every month. The A elements, we rotate them every 2 months. B elements every 3 months. C elements every 6 months. And D elements once a year. We do this with the objective of reducing our inventory level. With this cost distribution, we know that we have 2 sides, positive and negative. The negative one first is that several suppliers nowadays have the power to define which is the cost of our product structure, the suppliers of those A+ elements and A elements. The positive side is that if we are able to reduce the cost of these A+ and A elements, the total cost of the product structure will decrease in a huge way. So, taking into account the production challenge that was for us producing 1,000 power packs in 7 years, on 6 years, with several production phases of 8 power packs per month, and taking into account also the huge complexity of managing this type of structure, we really see that we needed an operational transformation. At the time that the contract was signed, this was the state of the operations in SAPA. We had a traditional MRP system, a manual logistics system, an outdated ERP. We had lack of integration between the PLM and the ERP. Our manufacturing routes and the machinery was really outdated, and we had no reliable KPI system. So here we have a timeline with the main milestones of the last years. In the year 2002, the company decided that they had to invest in having own product, in developing own technology. In the year 2003, we had our first operational model. And in the year 2006, with this first operational model, we produced our first prototype transmission. And in the year 2013, after continuing developing technology, we had our first production program that was called, that was an around 200 units production program. And that all operational model that we have at the moment was enough for producing those 200 transmissions. But in the year 2020, and after signing the huge 8x8 production program, really an operational model transformation was needed. As I have said before, at the moment of signing the new contract, the company had the capacity of producing around one and a half power packs per month. And 4 years later, last September, it was our first 8 power pack production month, which was for us a huge milestone. In the year 2020, we defined that second operational model. In the year 2023, we went live in the new digital system, and in the year 2024, at the beginning of this year, we went live with the new physical system. Those are the 3 areas in which we have focused our operational transformation. The first one, and the one we think is the most important one, is this: organization, people and processes. We really needed to start with our most important resource, that is our human resource, and by transforming the processes around the organization and the human resources. And then we started defining the digitalization and the physical production system transformation based in that organization transformation. Well, very quickly, talking about the physical production transformation, 2 main things to say. We have improved our assembly areas. Now we have an assembly area for the transmission and for the power pack, and in both lines we have an area where we assemble several decoupled sub-assemblies that we have in the structure, and in the right side we integrate the transmission in the transmission integration line and the power pack in the power pack integration line. At the end of both lines, we have our test cells, because every product that we deliver to our customer has to be previously really tested. Then we also have made huge improvement in our machining plant. This is the new layout that we have. We have made investment in having new machinery for those internally machined references and new machining routes. And we have reorganized the whole machining plant in machining cells. We have O-ring machining cells, external teeth gear machining cells, housing machining cell, and also hydraulic valve blocks machining cell. Another important thing that we have made in the machining plant is internalize several processes that in the past were outsourced, as for example, the treatments we apply to the parts. Now we have a nitriting and heating treatment area. That is the one that you can see here, where all the ovens are. And with this, we have been able to reduce a lot the lead time of these references. Talking about digitalization and IT transformation, we have changed our ERP. Now we have Microsoft Dynamics 365, where a lot of operations of our production and supply chain management occur. And then we have several satellites around the ERP which perform several specific tasks they are specialized in. We have B2Ys to managing all of our planning module, and we have implemented demand-driven, as you will see later. We have the Siemens PLM to manage our engineering structure and all the drawings. We have also implemented a warehouse management system, which is called SGA, and which connects with the ERP. In the past, our logistics system was really, really outdated. We have a really manual process, and there was no investment in both the warehouses and the processes, and we have invested a lot in this. We also have introduced MES of Siemens to plan control and work orders control. And then we are creating several workbenches with main KPIs with Power BI. It is important to say that doing this type of integration has been really, really difficult. Each system uses different controls to transfer information with the ERP, and we have had several problems, but we are quite happy with the result. There is a lot to improve, but it hasn't been an easy process. As we are in the demand-driven world, we have to talk a little bit of how we have implemented demand-driven in our planning model. Maybe some of you are thinking that if we have fixed demand, we know that we have to produce 1,000 power packs, why are we introducing demand-driven? Well, that is because we have a lot of supplier, production, and internal variability. We have variability because we have a lot of problems with our supplier performance. We have around 250, 300 different suppliers in both the European Union and the United States for managing that 50% of our structure. We have a lot of supplier dependency, also a lot of lead time variability. Our internal machining routes are really complex. We really needed to have a synchronization in the flow of the materials, and as you have seen, our product structure is really complex. So that is why we need demand-driven. Every time we start a new program, and every time we start defining a new operational model, this is the operational diagram definition that we follow. First, we decide whether a reference in the structure is going to be outsourced or internally machined with our make or buy strategy. Then we create our operating strategy diagram. We select our system drum. In this case, our drums for the 8x8 production programs are located in the assembly, in the test cells that we have after the power pack and after the transmission integration line. And also in the machining plant, they are located in our most constrained resources that we have in each manufacturing cell. Then we subordinate the system to those selected drums. We choose our decoupling points. Our decoupling points are located in all the outsourced references and in all our internally machined references. And then also we have, as you will see later, several decoupling points in some sub-assemblies that we decouple and we manage previously to the final integration. And then we build our buffer profiles with the techniques that you all know. This is our decoupling strategy diagram for the transmission and the power pack assembly lines. It's in Spanish, but the blue one will be the transmission integration line that has 5 main stages, and the green one is the power pack integration line, which has 8 main stages. After both integration lines, we have our test cells that, as they are our drums, they are managed with some time buffers. And after the transmission integration line, you will see that we have a decoupling point of assembled transmission to mitigate problems that we could have in the transmission integration line and to not have those problems later in the power pack integration line. And then we have those 7 decoupled sub-assemblies in the integration line of the power pack and 13 sub-assemblies which are also decoupled in the transmission integration line. Machining plan operational model, okay, those are the references, the reference families that we have select to be internally machined in our machining plant. We machine internally the O-ring gears, the external teeth gears, the hydraulic valve blocks, and also the housing of the transmissions. We have selected those references because are the ones we have more know-how in, and the ones we think that we are better doing than the external suppliers. In collaboration with V2Wise, we have implemented a methodology that is based in the theory of constraints to manage that machining plant. First of all, we have analyzed all of our manufacturing, of our machining routes, and we have divided those routes in two. The first part of the route goes from the raw material to a semi-finished reference. And in that part of the route, we have a bottleneck, a constrained resource. Then we have the other part of the route that goes from the semi-finished reference to the machine reference, where also we can find another bottleneck. What we do, and I will try to explain it very quickly, and if you want to comment anything more of this, you can later talk with me or with the V2Wise guys. What we do is we schedule the capacity in those both bottlenecks, and we subordinate the work of the rest of the machines in the cell to that schedule that we have in the bottlenecks. And in the rest of machines in the cells, we manage with time buffers. And we know that if we do a good management of those time buffers, the part will be in the bottleneck the week that has been scheduled. Last, operative results. Well, those are the main operative results, but I think that, well, I know that the operative results are even better than the ones that you can see here. We have had a 20% reduction in our inventory level, but this is the last 4 years. If we hadn't used demand-driven, I know that the reduction of inventory will be more than 100 or 150%. We have had a 40% reduction in our lead time of delivering our products, both the transmission on and the power pack. Planning time has been reduced a lot. It's way easier to plan now with the demand-driven and the operational transformation. And for me, one of the most important ones, we have had a 40% of reduction in stockouts. In the past, it was really usual for us to have stockouts because of the complexity of our structure and the lack of maturity that that structure has had in the past. And it was very usual for us to stop the assembly line because we have stockouts. And if we don't have one bolt or one washer of those 10,000 elements, of those 1,300 SKUs, our assembly line stops. So every reference, even if cheap or expensive, is very, very important for us to manage. And with this implementation, we have reduced the stockouts in a 40%. Future challenge. Our main objective is to stabilize the system back in SAPA operaciones, stabilize, continue improving, adapt this new operational model to different range of projects that we have, engineering to order projects, make to order projects, other type of projects, and then try to replicate this operating model in our SAPA transmission plant and become suppliers of the US Army for high production programs that they will have in the future. So thank you. This has been everything.